Arrhenius equation. This one builds off our relation of temperature and rate to do this in a bit more systematic and equation way, where we can go through and actually calculate how our reaction rates are going to change, instead of just discussing casually how one will go up as our temperature change. Now, let's think about what we mentioned in previous videos. As our temperature increases, our rate is going to increase. But let's think about what that means for our rate law. Our rate law only had rate and concentration and K in it. So if we don't change our concentration, but our rate changes, that means our K has to change. So this video is going to be walking through that idea, that our temperature is going to actually change our K. So our Arrhenius equation is going to relate this for us. So it relates temperature to the rate constant. Now you'll see this in a couple of different forms. The first one I'm going to show you we don't actually use that much. However, from a derivation standpoint, it's probably the most useful one. So this is the Arrhenius equation, as you'll usually see it written if you just simply say Arrhenius equation or Google the Arrhenius equation, where we have K is equal to A, E to the EA over RT. So we can see that we have the activation energy in there. We have R, or the gas constant, and we have T. Now, this is nice in terms of relating EA and K, and T and K. But what it doesn't actually tell us is allow us to calculate one K from another, or look at changing numbers. So what we can do is play around with a little bit of algebra here. And we can take the natural log of both sides. And now we're going to take and separate these two things out. So we see we have EA over R. I'm going to pull that out, and I'm going to pull out 1 over T. You may say, why am I doing this? Well, I'm doing this to separate out our variables and to show you something very useful about what a graph of this looks like. So if I do this, now let's think about what each one of these are. If we look at the natural log of K, for a given temperature, we call K a constant. But here, we're not at a given temperature anymore. We're changing our temperature, and our change in temperature is going to change our K. So that's actually a variable. As I just said, we're changing temperature, which means that 1 over T is a variable too. All right. Activation energy isn't. Activation energy is our set energy for our given reaction. R is a constant. It's the one here that's always a constant. And I haven't really talked about the natural log of A. It's not going to come up a lot. But A is a constant here too. Well, if we have a variable equals a constant time of a variable plus a constant, we could rename that y equals mx plus b, and we have another linear equation. And so this is really useful from a laboratory standpoint, because we can graph a series of reactions where we can measure T for various different T's that we want to measure. We can measure K, and we can use this to solve for our activation energy. So let's just take any random graph here and look at this again. So we know the equation of a line is equal to y equals mx plus b. We also know that we have this Arrhenius equation written out in a way that gives us a linear graph. Now, it doesn't give us a linear graph if we just do T versus K, right? We need to treat each one of those as a kind of combined variable, a kind of complex variable. So look at our x-axis here. Our x-axis here isn't T, it's 1 over T. If we look at our y-axis here isn't K, it's natural log of K. But if you set up your graph like this, now you get your linear equation. And you'll do this in lab. So now if you look at this, what's your slope? It's that entire group that I'm calling n, right? So it's negative EA over R. That's your slope. So we can use this to find our activation energy, because if we graph this, we can simply solve for our slope. Excel can do that very easily. And now we can find EA. So this is typically how you would go about it in a laboratory setting. So this might be a really useful video to have on hand when you do that sort of thing. That being said, because it's not always conducive to have a laptop with you with full Excel functionality where you can graph all of this data, it's also useful to just have a 2-point formula. In a lab, you would never really only want to do this with 2 points. But from the perspective of problem solving, if you already know for sure some of the data, it can be really useful. And so that's kind of the direction that we take with it in a lecture course. So we're going to do an example. But in the process of doing this example, I'm going to actually derive what we would call a 2-point formula for this. When we go to do that, then I'm going to circle it so you know for sure that's our 2-point formula. And that's what we're going to use to generally solve these equations. So I like doing the derivation for you once to see, but you don't want to start from here every single time. So first, let's look at the question and think about why we would want to use this equation for this problem. So we have a rate constant, and I tell you that it's a second-order reaction, and I give you the reaction. I tell you some numbers. I tell you your temperature. And then I ask you to calculate the activation energy. So we know K and T. Now, you might be saying, but I don't know what A is, and you've hardly talked about A at all. You'll see why I don't talk about it all that much. In the last example where I showed you the graph, you notice it never came up. And by the time we get done with it in this 2-point formula, it's not going to come up either. So let's take this and do a little math trick that we can do to make 2-point formulas. We're going to subtract each side, right? So we're going to take the y side of the equation, the natural log of k, and subtract those from each other. And then we're going to do the same thing to the other side. So it's a little messy. You may need to pause and take a minute and kind of trace where everything is going. But take a look at this. So on the left-hand side, we have our natural log of k1 minus k2. And on our right-hand side, we have the whole equation. But notice on the t, I put a subscript. So again, t1 minus t2. So this is obviously a bit messy, but we can do a lot of rearrangement to make it into a much nicer equation. So first off, let's look at the left-hand side of the equation. We have the natural log of k1 minus the natural log of k2. Whenever we do a reaction, or whenever we do a natural logarithm, we can go ahead and say, well, if there's subtraction, that's going to become division. So subtraction of a natural log becomes division. So we end up with natural log of k1 over k2. Now, if we look at the other side of this, our right-hand side of this, EA and R aren't going to change. So we can factor that out of the equation. So that's where the negative EA over R comes out. Now, if we look at our natural log of A, that's in both of those. A is also a constant. Now, we can't factor those out because they aren't multiplied, but they're going to cancel out because our natural log of A on our first side minus our natural log of A on the second side means that they're just going to cancel to 0 because you're going to have a number minus that same number. And so they cancel and they don't show up in the equation. So we end up with negative EA over R times 1 over T1 minus 1 over T2. Now I want to make a quick note about how you'll see this equation written. You'll see it written 2 different ways. Oftentimes you'll see it like I have here. But there's several different algebraic rearrangements that you can have too. For instance, you can have K2 over K1. But if you have that, the other side of the equation will be 1 over T2 minus 1 over T1. So basically you'll distribute a negative across the entire thing. It's a pretty common way of writing it. Sometimes you'll also see the negative from the EA distributed into the T's. So lots of different algebraic rearrangements. It doesn't matter which one you use. Now this is your starting point for most of your actual problems. Normally I wouldn't start from this first set and work my way down. I just wanted to do that so you could see it done once. So let's go ahead and work through this. So I could just fill in, but I could also rearrange for EA. So I'm going to go ahead and rearrange for EA first. So if you work through this and you do all of your rearrangements, and again, you'll see this rearranged in a variety of ways, so don't let any of the directionality of things mess with you too much. And you fill in all of your numbers. I'm going to just pause for a second so you can kind of trace where everything came from. Notice your R, we're using 8.31. For your temperatures, make sure you convert into Kelvin. In this case, I gave it to you in Kelvin, But if I had given it to you in Celsius, you always have to remember to do that conversion. You can pretty much never, ever, ever be lazy with that conversion. And then for our natural log, we have our 2k's, and we can divide those on top of each other. And when you get all done with this, you get a number. So it's effectively just a very large filling in question once you get to this initial point of this 2-point formula. So for this one, we're going to start from the same place. We're going to start from that 2-point formula. Now, I don't give you k's here. I do give you one temperature, and I tell you we're solving for the other temperature, but no k's. But we have to use what we know about what k is in terms of the reaction rate. We know that k is proportional to the reaction rate. So if K2 is related to K1 in the same way that rate 2 would be related to rate 1, we have some information we can use now. So the reaction is 8 times faster, which means that K2 is 8 times as great. So instead of looking at K2 and K1 and saying, well, we don't have that, we have the information to fill in there because K2 is 8 times as big as K1. And so we can fill in the natural log of 8 for that. So we fill in the natural log of 8 for that side of the equation. And then for the other side of the equation, we fill in just as we did last time. We need to make sure to watch our units. And so we multiply by 1,000 for our activation energy. That's very normal, by the way. Typically, activation energies are given in kilojoules. So you'll almost need to do that, I'd say 90% of the time when you're doing these problems. So you have your divide by R as 8.31. And then your 1 over T2 minus 1 over 305. You'll need to do the algebra rearrangement to deal with this. So I'm going to go ahead and write that out to show you. So you multiply your natural logarithm of 8, multiplied by your R and divided by your EA. And then add in your 1 over 305. And that gets you 1 over T2. You type that all in. I did it this way to show you this is normally how I go about it because I can solve that all as one thing. And then I can do 1 over inverse in my calculator. Of course, you are welcome to do the algebra however you want. And we get our answer. So to quickly summarize up what we did, we use the Arrhenius equation to determine the activation energy in K for a given set of data. As temperature changes, our reaction rate changes, and that means our K has to change as well. And the Arrhenius equation gives us a way of relating these two. We can do this with a graph, as we did earlier on, or we can do this from a 2-point formula.